Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to walk through example 1 here in our notes about centripetal acceleration and centripetal forces. So what we're looking at, we have this car that is driving along this curvy path here. And for the sake of this example, imagine the road is level and the car is driving at a constant speed of 10 meters per second, or I guess the car doesn't drive. We'll say the car is moving at a speed of 10 meters per second, which is not changing in this example. Now, what we're going to do is we're just going to draw and calculate frictional forces acting on a car at positions shown. Whoops, sorry about that. There we go. All right, so when we look at this position right here, what you really need to realize is that before that position, the velocity vector of the car is looking something like this, and afterwards something like this. So the velocity direction is changing, and that means that the car is accelerating, and hopefully we recognize what type of acceleration that is. Right, that's what's known as a centripetal acceleration. So if I were to draw a free body of the car top view, the frictional force is what's causing that acceleration, and it must be pointing roughly something like this. Now, I'm actually ignoring air drag for this example. I mean, technically the frictional force is also working against air drag, so it has a small component in this direction, but I'm going to assume that went away. We're not going to worry about that for this example. Now, another thing I should take note of here, I've just made the same mistake I see lots of people do. I've drawn this frictional force vector and I ended it here, and that was just kind of by accident. The length of that force vector has nothing to do with the distance of the radius of curvature there. In fact, it doesn't even make sense to compare them. And I shouldn't say nothing to do with it, but what I mean by that is the length you draw that vector does not need to correlate to this distance. So I'm going to go ahead and draw that force vector maybe a little larger, maybe something like that. And if we calculate that, this frictional force is causing a centripetal acceleration. So it's going to equal mv squared over r. And I think what I'm going to do here is save myself a little bit of writing. I'm just going to put in values here and crunch a number. The car is 1,500 kilograms and moving at 10 meters per second. And the radius of curvature at this location is the one that's called R1 here, 20 meters. So I'm going to go ahead and calculate a value. And I get 7,500 newtons at that location. All right. Now let's look at the second location here. And what I'd like you to do again is try to imagine what's happening to the velocity vectors. So sometime before this location, the car's velocity vector is pointing this way. And sometime after, it's pointing this way. Oops. So notice that the change in velocity is like down and left towards the center of curvature. So that car is undergoing what we would call a centripetal acceleration. And the frictional force is causing it, and that force is pointing something like this towards the center of curvature. Now you notice I drew that vector a little smaller than I did the first one. And the reason is I'm recognizing that this location has a larger radius than this location. So I know that the v squared over r term is going to be smaller at that location. So if we crunch a number, again, equal to mv squared over r, and I put in a numerical value, 1,500 for the mass, 10 meters per second for the v, and 50 meters for the r, I get 3,000 newtons at that location. All right, let's look at the third location. That's this one. Now, you'll notice at the third location, the car is basically going straight. Well, you could think of a straight line as a curve with an infinite radius. So mathematically, when you look at v squared over r, if the r is like infinitely big, the v squared over r term is 0. So long story short, this car is not accelerating at that location because the car is moving at a 10 meter per second speed that is not changing in this example. So that means that the tangential acceleration is 0. And the velocity vector, here's one like, right before this instant, let me call it v1, and here's another velocity vector after the instant shown, I'll call that one v2, and again, notice they are not changing in direction. So this car is not accelerating at all here. So ignoring air drag, there's no reason to put a frictional force in there at all, so I'm going to consider this example done. I hope that this helps you understand centripetal forces and how to put them in free bodies. Have a great day.